Hi everyone, and welcome to our webinar, Machine Learning, the Truth, the Whole Truth, and Nothing But the Truth. I'm Liat, I'm the CMO of Recognize, and I will be your host for today. With me, Chen Linchevsky, our CEO, and we're going to discuss the technology of machine learning and why and how it is fitted for the process industry. If you have any questions, we invite you to write them down in the dashboard, and we will be happy to address them after the presentation. And with that, I hand it out to Chen. Good morning, Chen.
Good morning, Liat, and thank you. Today we're going to briefly speak about machine learning. It will not be the regular presentation of SamGuard and our solution, but the more general view of how we see machine learning and its applicability to the process industry. So we'll start by briefly discuss the need, what we think our customers, or what we hear from our customers that they need, what they are trying to achieve by using analytics. Then a little bit about, or more than a little bit about, the limitations of machine learning, without depressing anyone, but just to give a clear view of what's possible and what's not possible. And then, given the need and the limitations, try to see what's the action plan. What can we do? How can we proceed with this journey of actually using the data that we have and applying predictive analytics for our process plans? So just a word about us. Recognize is focused on predictive analytics for the process industry. We work mainly with chemical, petrochemical, refineries, other oil and gas installments, pulp and paper, and so on. We believe that this industry, and I'll talk about it later on, has a very specific needs or circumstances or conditions which are very different from other industries, and therefore the solution need to be fitted exactly to those to this kind of environment. Now, in terms of the need that we see in the industry, is that we see a clear focus on more production. If people 2-3 years ago were talking about reducing the maintenance cost, prolonging the lifetime of a part, what we see in the recent years is that the focus is around how can we produce more, how can we avoid failures, downtime, blockages, and manufacturing in the lower quality, and so on. Okay. So the focus is not so much about only the maintenance, but the maintenance is actually an instrument in order to get to more production. And this is something that most people tend to summarize in the term OEE, overall equipment effectiveness, which kind of capture the availability, the performance, how stable it is, quality, and so on. So if we're talking about applying predictive analytics, we're actually not necessarily talking about the maintenance aspect, but we're looking at the overall performance of the plant. And if we look at the overall performance of the plant, it means in most cases that we need to look at it holistically. We need to look at the entire plant, because if our focus was maintenance, maybe by just looking at the most expensive compressor, we would be okay. But actually, the problems that may affect our OEE can come from everything. Come from the compressor, but it can also come from the tank, from the catalyst, from the valves, from condensers, from the combination of all the above. So basically, we're required to look at the entire plant, at all the equipment, at all these thousands of sensors, which most plants currently have, in order to eventually improve the bottom line. Okay, and for that, we want to use the machine learning. So with that, let's talk about what can we do and what we can't do. So if we look at our plan, so we already said problems can occur everywhere, and of course we have plenty of data. Okay, we have hundreds or thousands or tens of thousands of sensors for almost every asset that we have in our plan, and sometimes we have redundant sensors in cases where it's important. So we have thousands of sensors out there. So we have the need, we have the data. The one thing that we don't have in the process industry, this is where it's very different from other industries and other cases, is that we have only very few historical examples. Okay, so if we look at the process plant, probably most of the valve, pump, and so on never failed. If it failed maybe once or maybe twice. And once it was in the winter, once it was in the summer, completely different conditions. So actually, the environment that we're talking about is environment with the data, but with just very few historical examples. And this means that if we're trying to predict a failure based on historical cases, which is what we do when we use supervised learning, we're doomed to be unsuccessful. Okay. If we look at the rule of thumb for being able to predict a problem, let's say we need something like 30 examples. Okay, so if we're talking about 30 examples of pump failing, and it was under the same operation conditions, not that once it was when the plant was operating in full force, and then when it was operating on half of it utilization, and that it was for the same equipment, and so on and so forth. And if this exists, maybe we can do supervised learning and try to predict when this specific problem will occur next time. But in most cases, we don't have these 30 examples. And even more important, we don't care about the past failures, because they probably will not happen in the future. Okay, because if we had a failure and we fixed it, in most cases it will not happen in the next 5 years or 3 years, or I don't know how long. So actually, in most cases, we don't have enough examples, and the failures that happened in the past are not necessarily the failures that will occur in the future. From statistical perspective, we cannot predict it, but even if we could, it wouldn't bring us much value. And as our head of research, Dr. Ilana Chlieli, likes to quote Tolstoy, happy families are all alike. Every unhappy family is unhappy in its own way. And we tend to think that it's the same thing with failures. Every failure is a new story. Okay, so predicting the next failure based on the historical failures is not very likely to succeed. And just to give you a little bit of examples, so we will talk more through examples. Let's assume we have a banking case, okay, not a process industry case, and let's assume that we have here 6 people that took a loan, and we're trying to predict when the person will not return his loan. Now we see that on the last column, like you need in the case of supervised learning, we have a labeling of the event. We know that this guy from New York City with income of $1 million, he's the only one here who didn't return the loan. All the rest of the people were okay. It means that if we try to build a supervised learning, a prediction model based on that, we will probably get to a situation where we think that one of the items that is influential in terms of determining whether a person will return a loan or not is a higher income. Okay, because we see that from our examples here, and this is the only thing we have. Okay, we don't have common sense, we don't have any other knowledge about banking, but from the data that you see on the screen, this is the most probable conclusion. So when we get the new group that you see here on the bottom, and there is this new guy from LA, and he's also making $1 million income, we will assume that his less likely to return his loan compared to somebody else from New Jersey who's making only 60,000. Okay, because the only case that we had for a person not returning a loan is this guy from New York City who's making $1 million. And so basically, in order to make it, now if we had 1,000 cases, 2,000 cases, 3,000 cases, probably this one case of the guy from New York City will be somehow melted into all the examples that we have, and will not get such a high weight. But if we're looking at 1, 2, 3, 4 cases, actually this is what we have, and we're most likely to be mistaken with our prediction. And just to finish this subject about supervised learning and the ability to predict failures, I will give another example from a different industry or from a different area and a little bit of different problem, but again, to give you a feeling of the potential problems with trying to apply prediction. This is a MIT technology review, which says that AI is sending people to jail and getting it wrong. Now, the thing is that what basically happened here, and this is written in the article, is that the learning group included much more Afro-American people than others. As a result of that, of course, the probability of an Afro-American person to be ranked as a probable not to return to jail after getting bailed is much higher, because the number of cases in the training data is much higher. So the takeaway that I want to make here is that keep in mind that as much as supervised learning is smart or it's just as smart as the training data that you have. And if you don't have enough examples, or if your examples are biased, the results will be exactly the same. Okay, so if I get it back to the things that we're seeing in the industry today, we're seeing more and more cases where we get RFQs or RFPs where the requester is giving some training period with few failures, some hold up period with another few failures, and then the testing period, and he's asking, okay, can you identify those failures? And this assumes, okay, this method assumes that you're going to apply supervised learning. Now, since I think I kind of made it clear that supervised learning cannot work if you have only few failures, it doesn't make sense to test the tools by means of supervised learning. Okay, so if you have few cases, supervised learning is most likely would not work, and therefore testing different tools based on the method that is most likely not to work is kind of a thing that I would not recommend as a plan forward. And just as a remark here, there are methods which are trying to build predictable models based on very few learnings, but at least for now, even the academic environment, the results there are not something that you can say, okay, based on 1, 2, 3 examples, I can actually predict the 4th and 5th case. So I would assume that it will, if at all, it will take years before this will be implementable in the actual industry. Okay, so problem can occur everywhere. Plenty of data, few historical cases. We cannot do a specific prediction based on that. Doesn't matter which tool, doesn't matter which vendor, it doesn't matter if you're using the best machine learning running on Google or on Azure or on some other tool. If you don't have the cases in your training data, it's just not predictable. So if this cannot work, what can we do? So what we can do is we can basically try to define what is normal for your plant. And then, of course, give you alert when something is abnormal. And of course, most of the time, and this is the assumption, most of the time the plant is normal, so we have enough time to learn what is normal, and then provide the alert when it's abnormal. Now, this is sounds fantastic, and there are many people who are saying, just give me the data and I'll show you where there are anomalies. And it's there are algorithms doing that on the internet, and it's pretty simple to implement. The only big problem about using this method is that it creates a lot of noise. Not everything which is anomaly in the data is actually problem in the plant. And to give you a better understanding of what we mean here, let's look at the table here with two sensors that can be in two states, 0 or 1. If you look at the different possibilities of states for the entire plant, you actually have 2 in the power of 2. Okay, you have four possibilities for that. And just to give you a little bit of feeling, then the number of atoms in the universe is 2 in the power of 86. Now, so this is the case where we have 2 sensors. Now think of the case where you have 1,000 sensors, okay, or 2,000 sensors. So actually, and each of them have only 2 states, 0 or 1. So actually, the number of states that the plant can be in is 2 in the power of the number of sensors that you have, which is a huge number, more than the number of atoms in the universe. Okay. Now it's even worse than that, because it's not a 0 and 1. I mean, there are sensors measuring the temperature or pressure or whatever, and they have multiple values. So actually, the number of states that the plant can be in is is huge. It's just huge. And there is, if you look at it, there is no actual normal state. Okay, everything will be a little bit different than it used to be, and this is just mathematically proven. It's not related to whatever tool you're using. If you're trying to identify anomalies within an environment of more than these 2, 3, 5, 10 sensors, because the number of states is so great, you're going to get hundreds of anomalies for every new line of data for every new minute. Okay, because there is actually no state of normal. Now, it's even worse in the case of a process plant, because actually the data is finite. Okay, if you look at let's say data in other environments like Google, all our web surfing data and so on, there are many lines. There are billions of people that are using Google, and there is a lot of information. If you look at the plant, okay, we have those thousands of sensors, but how many measurement points we have? We actually have, let's say we had the maintenance last year, so probably the information before the maintenance is not relevant. So we have 1 year, 365 days, 24 hours, 60 minutes. Make the calculation. Yeah, there is some data there, but it's not endless amount of data. Now, given the number of states that the plant can be in, and given the number of lines that represent the historical states, you get to a conclusion where the assumption that machine learning is doing, that there is a random sampling, is actually not the case. Okay, we try to apply machine learning into an environment which does not really represent all the normal situations. Okay, and this is a situation. I mean, this is the thing. So if we apply machine learning into our environment of a process plant, where we have thousands of sensors on one hand, and we have limited amount of data, we will find ourselves in a situation where we have many anomalies. And again, there may be more in using one algorithm and less in another algorithm, and there will be more if you set the cutoff to a certain number, or less if you set the cutoff to a different number. But the overall is that these are anomalies, okay? And these anomalies are not really representing the plan. So the situation when you apply machine learning, you cannot apply supervised learning because you don't have enough cases in the past. But when you try to apply machine learning, you get a lot of noise, many anomalies, which are anomalies by the measurement of the machine learning, but are not really representing a problem. So what some people do in order to avoid that, they say, okay, we understand our limits, so let's take only few assets, and for those few assets, clean the noise, check the different situations, and find exactly which tags we want to include and which tags we don't want to include, and clean some states of the plant which are not relevant, and so on and so forth, and work a lot manually together with the operation people and looking at the data in order to build a model for this specific asset. And this can work. The only problem is it's not scalable. Okay, the fact that you can do 1, 2, 3, 4 assets within your plant and build a very good model for them doesn't mean that you can scale it to the thousands of assets that you have in your plant. It's just not scalable by the effort, by the time needed. It's not scalable. Okay, so this is basically the situation given the current machine learning model, the current machine learning methods, and this is where we this is a situation where we found when we actually started. Okay, and when we analyzed the situation, we thought there is another source of data. Okay, there is another source of information. Okay, and this source of information, in the case of a process plant, is this ability, this knowledge of the plant, which does not exist for Google. Nobody really knows what's going on the internet. It doesn't exist in other cases, but it does exist here. Okay, now if you take this, add this context, okay, this knowledge of the plant, and add it to the machine learning, then you're actually getting into the situation that you may be able to determine which of these anomalies are relevant and they represent the problem and which are not. And this is exactly what we're doing with SamGuard. And again, as I said at the beginning, I'm not going to give a full presentation of the product, which of course is available, and you can contact us for that. But I would just say that the big thing here is to create a domain model, which is very, very simple, fast, doesn't require any conceptual modeling skills, doesn't require anything other than decent understanding of the plant, which a process engineer would have. And by creating the domain model, we're able to add another layer on top of the data. Now, this layer, which the domain model is basically speaking the language of the people, this layer is turned within SamGuard into a graph. Okay, and now the graph is something that we can use mathematically and automatically together with the machine learning in order to avoid all those problems that we talked about before. So we can address the sparsity of the plant, the number of potential tags, potential states of the entire plant, and do a better division of the plant according to this graph. We can then aggregate the anomalies which are created and aggregate the anomalies according to their causality in order to determine which anomalies are really representing problems and which anomalies are just anomalies. Okay, it's a state that that it's maybe not normal based on machine learning, but does not represent the problem. Okay, so there are ways of taking the machine learning and enhancing it and making it better and presenting only the few things which are relevant to the user and not the hundreds of anomalies. Okay, these ways, like the way we're using, is not coming from inside the data, and it's not coming from having a deeper machine learning algorithm. Okay, it's coming from the understanding that the conditions of this industry are different from the conditions of other industries, and therefore require different means in order to provide the best possible results. Okay. Now, given our solution, and I can say, testify that it's working very well in terms of providing the right alerts. Even then, we have to understand that when you're applying machine learning, it's not it's not a recipe. Okay, it's not that I'm trying to predict something that happened 1,000 times in the past, and therefore I know what I should do if it comes again. Here we are actually looking for problems that most of them never happened in the past. Okay, so if we're looking at machine learning and setting the expectations for machine learning, we have to understand that at the process plant, machine learning or using machine learning, using analytics, is a combination between the capabilities of the mathematics of the software and the capability of the person who is analyzing the alert. And at least for the near term, we don't see this person getting out from the loop, and we don't see the software recommending do something for a situation that never happened in the past. Okay, so if you understand that, actually what we're trying to do with predictive analytics is actually to provide you a flashlight, okay, not the cookbook, not the recipe, then you're one step into success. Because think about it, you have thousands of tags there, hundreds of potential problems. If I promise you, listen, we'll give you a flashlight and highlight where you need to focus your efforts now from all these thousands of sensors, this is a huge help for the operation people. Maybe it's not perfect, we're not replacing them, we're not telling them what to do, they still need to think, but it's a huge step forward in order to avoid those failures and improve the OE. Okay, so instead of looking at thousands of potential or of tags and hundreds of potential problems, this flashlight, this direction, is a huge step in the improvement. But we don't stop here, okay, because still there are things that machine learning can do in order to improve this part of human understanding, okay, and it will always be, or at least for the near future, we will need the human to get involved, to understand the problem, and then to decide how to act. Okay, it will not, and I can tell you from all the customers that we have, from all the implementations, for all the many plants that we're installed here, I never seen that we give an alert. The user doesn't understand it, but he says, "Okay, I have an alert. I'm going to replace this pump." Okay, it doesn't happen. The user need to understand what is the problem and therefore act accordingly. So we do our best now, or our focus now is how to help the user understand what the problem, understand what the flashlight shows him, and then act accordingly. What we do here, we try to personalize the alerts not by supervised learning, but by semi-supervised learning, meaning that every time a user is looking at the tag and marking whether the tag is helpful or not helpful in the context of a specific problem, the machine learning is taking this into the calculation, and the next time an alert will come, it will actually make a decision which tags to show the user based on the previous feedback that was given. Okay, so we actually take the feedback that the user provides as you use the system in order to improve and improve and improve. And in the next version that we're going to release in 3 weeks from now, we're actually taking this a step forward, and we're trying to guide the user through the analysis process. So we all the time show only very few tags and show exactly where you should look at, and then the user can say, wow, good, or discard. And based on his or her answer or feedback, we'll decide which other tags to present next, and which other tags to present next, and which other tags to present next, until the problem is completely clear to the user. Okay, so we're taking, we're trying to personalize and provide the best alerts using the feedback that is provided to the user. So now it's something that we do for the next event, and actually in the next version we're taking this feedback and applying it in every tag and every period that we show to the user. Okay. Now remember that this is part of the learning. Okay, here the machine, the software, the machine learning is actually learning from the feedback of the user. Now you can say, oh, there are so many limitations, or it's only a flashlight, it's not a cookbook. Let's wait. Actually, these learnings that we're getting now, the improvement that the software is making through your feedback, is something that if you don't start now, you'll never get it. Okay, I assume that you're not going to get more failures in the future. I assume that the only way to really improve is to start now, provide the system feedback, getting better and better and better until you get to a certain level of perfection as we move forward. And in that sense, I would want to add another aspect, is that we said earlier that using supervised learning in order to predict the future when you have only a few cases is unlikely to succeed. But you can use supervised learning in order to learn about the past. Okay, to do postmortem for cases that where you had a problem. And this applies for cases, for example, where you have problems with quality, or you have blockages or things like that. It's less likely to succeed when you're talking about a part failure. But in those cases where you have repeated cases, then you can do this postmortem. And here again, machine learning can help you. Okay, you're not expected to mark down all the cases where you had quality which was not good, or all the blockages and so on. Actually, what we're applying here is we're applying active learning technology, which allows the user to only mark few examples, and then based on that, we're showing more examples which may be exactly the same case, or some examples which the system thinks are most likely to be wrong. And based on the feedback, we actually built our history. Okay, so there are things to do even when it comes to supervised learning in order to enrich the history. So it will not help you so much to predict the next failure of the valve, but it does help when it comes to another case of doing postmortem, or understanding the root cause for problems which are repeating themselves, such as quality blockages and so on. And because we think this is so important and this is so valuable, what we actually implementing now and this will be available in the version after the next, which is planned for September, is what we call the Sandbox. The Sandbox is actually something we're doing now offline, but will be available with the user interface. So the user can actually create different experiments for different periods and try to determine the root causes for that. And this is kind of a combination of all the things that we talked earlier, the feedback of the user. Some things are supervised, some other things are the machine learning is running unsupervised in the background. And this brings all those great methods in a situation that they can work, okay? And this is, I think, the most important. Use the right methods for the right application. Do not try to use supervised learning where you have a few cases. Do not try to use pure machine learning and anomalies where you have thousands of sensors and you don't have any way to limit the noise. And the Sandbox is really a good example of how to implement the right methodology at the right place. And with that, I want to move to the last topic of our conversation today, and this is how to test the technology. Okay, because if we understand now what are the limitations, and we understand that it's a journey that you need to start, and eventually will bring value, you need to start it in the right way. Okay, and I think the one most important takeaway or the most important understanding is that actually the implementation of predictive analytics or any other machine learning project is a combination of both the analytics but also the operation people. It's not a statistical exercise. It's not something that we just do for in order to test our data. It's actually something we do in order to improve our OE. In order to do that and to show the value to the organization, we need to use both the analytics and the people. So all these attempts to say, okay, let's throw in some data with few failures and then see how good this vendor is or that vendor is, are not likely to provide you the right answer of how to move forward. Okay, it's actually it will tell you very little about this vendor, about the capabilities, and it will tell you even less about how much value it can bring you in the future. So what we do and what we recommend, regardless of the solution that you select, is that you do online implementation. And what we do when we implement SamGuard, we start with the impact analysis, which is true for every project, to understand what are the KPIs, what's the available data, try to give the operation people initial results so there will be appetite for more. Then we continue with the modeling workshop, which is something we need for our in order to implement the solution, as I explained earlier. But then the most important thing is to run online. And running online is the only way of actually really understanding what's needed from the operation people, how capable they are, what's the right place, is it the process engineer or the control room, how much time we really need in order to assess the alerts, provide feedback, and so on and so forth, until and what's the impact on the OE. Because after 3 months, you should have some kind of impact on the OE, and you can really come to management and say, listen, this is how much we think we can gain from using this solution. So when looking at all the limitations of machine learning, looking at the capabilities of machine learning, looking at the possibility of providing you a flashlight to your problems within this huge plant, the only real way in order to test the solution, the only real way in order to really prove the impact on the OE is to run online. And it does require people in the innovation team or the people who select to decide, usually 1 or 2 vendors that will get into this online exercise. but we just don't see any other way of really qualifying what can be, whether it can work, not whether your organization is ready for machine learning, and this is for me the right way to start the journey. And one comment here is that when you do this online run, there is a tendency to say, okay, we have many false positives, we have many false negatives. Now, false positive and false negative is of course relevant when you do supervised learning. Okay, when you try to predict something specific, you can say, okay, I gave an alert about this specific thing and it was wrong, or it was right, or I missed something. Now, since we do not recommend to do supervised learning because you don't have enough cases, actually you cannot judge what if the online was successful or not based on these terms of false positive or false negative. So what we recommend to do is we recommend to set acceptable number of alerts. Okay, the process engineer or the control room, they cannot handle hundreds of alerts from the machine learning tool. Okay, but if they can handle 2, 3, 4 alerts a day, this is the number you should shoot for. And once you shoot for those 3, 4 alerts per your plant, then test the improvement to the OEE, okay, during the period of the pilot. Because assume that you need to check those 3, 4 alerts. Some of them will be correct. Some of them will be correct statistically, but will not represent a real operation problem in the plant. Okay, but eventually, from looking at all these alerts, you will get improvement to your OE. And while you're assuming that, of course, you're not going to miss things that are failing and the software didn't catch. Okay, so if I conclude this testing thing, so we recommend to test online and to set your expectations first, of course, in terms of OE and improvement to OE, and then by setting the number of alerts which are digestible per day by the operational team. And if you match the number of alerts and you improve the OE, I guess everybody will be happy. So I would like to summarize this this talk by emphasizing the 3 points that we or the 3 takeaways. So first of all, make sure that you're not that you're running after the right, or you're selecting the right machine learning method that works for the given problem. Okay, and in our case of a process industry, supervised learning is not likely to work in most cases. I mean, I don't know, maybe your plant, you have many failures of the same thing under the same condition, and maybe this is the right method for you, but make sure you're selecting the right method for the given problem. Secondly, and this is again very important, align the expectations about the results. Okay, the whole analytics thing is a journey. Okay, for years you were collecting data into your historian and using it in, I would say, using it to some extent. We're starting a journey where this data will be the most valuable asset, but you need to set the right expectation. If you think that today the machine learning will give you the exact instructions of what you need to replace for the entire plant for problems that never happened in the past, you're wrong. We still need the operation people, and we need to give them time, give them managerial support, and so on and so forth, in order for this to be effective. And finally, when you decided to go in and start checking the solution, whoever the vendor will be, do it in the right way. Okay, do not do it based on the statistics classes that somebody took somewhere where they said we need to check training period against the running period, and that's it. It's not likely to work in your case. And in the process industry, it's very complicated, it's very complex. It requires people and software, people and analytics. And from our judgment and from the cases that we have done, the best way is really to run online and test the real impact and treat it as an implementation project, just like you're doing with other implementations. So with that, I will open for questions. So if you had any, you can type them into the chat, and I will ask Liat now to read us.
Thank you, Chen. Actually, not to the chat, there is a specific space for the questions, so if you see that, that's better. We do have a couple of questions here. One, looking towards the future. Do you think the machine will be able to replace completely the human input, or how much will it be able to replace?
Okay, so if I look into the future, there are several things that are happening. Okay, on one hand, I do not expect the plant to be less stable, so it's not likely that we'll get more historical cases that we can learn from. Okay, so but at the same time, I think that the use of data and the integration into the instrumentation will be much tighter. And at Perconize, as part of the Samsung group, we all the time look at this vertical connection between the actual equipment, the actual physical equipment, the ability to analyze data by using machine learning and so on. So what I do expect, I do not expect the human to be completely out of the loop, but I do expect more closed loops that will enable us to affect the control or affect some control loops or optimize some control loops automatically more than it is done today. And this is a process that will require us to collect more data from the devices, analyze it in a better way, involve also some knowledge from the equipment manufacturer, like we're involving in the case of Samsung for our flow control equipment. And that will allow us to move to the next step. It's not a matter of months. It's not a matter of the next version or the next version. It's a matter of, if I need to estimate, I would say probably starting being more seeing more effect of that in the term of 5 years or so. So I wouldn't worry about the job security, and I would see this as a journey. Okay, you start now with what you have, and you start using the data, and you train the people to start using the data, and there are more more relaxed, more knowledgeable about actually making decisions based on data, and eventually everything will improve. Everything will be improved, both the analytics part and also the ability to use that automatically within the plant.
Thank you. Another question is about the number of alerts. You said earlier that you aim to trigger like 3 or 4 alerts per day. How can you make sure you cover the most important things?
Okay, this is a good question. The whole thing, the whole method is built in order to pick or aggregate or understand from all these anomalies which ones really represent the problem. And for that, what we're basically using the model that the operation people build. So the operation, what we do during our implementation is that the operation people use a very simple user interface, and they build a model of their plant, which doesn't represent the problem, just represents what's the structure, what's the main processes, and where's data measured. in real time, it actually provides us some kind of causality. Okay? It actually tells us that if something happens here and something happens here and something happens here, probably it all lead to the conclusion that there is a problem there. So what we do is we aggregate those anomalies that are coming in from the pure machine learning, and we try to understand over time whether they all represent a problem. So from the thousands of tags, we have hundreds of anomalies, and then we try to gather them into very, very few alerts. And this is possible
What happens in those industries where a high level of rotation, there is a high level of rotation of employees?
It's an excellent question. The knowledge of the operation people is crucial. Okay, and this is, you know, it's crucial whatever analytics you do. And I think hopefully I convince you that just by throwing the data into machine learning engine, it will not bring you any real value or real result. So the knowledge is needed, whatever method you're using. What we try to do, we try to keep the minimal set of knowledge that we need in order to provide good results. And if I go back to where we were earlier, what we're basically telling them is that, listen, all you need to do is to set the plant structure. And this is something I'm sure the process engineer at any plant knows, and it's in the P&IDs, and it's in the process book. It's there, okay. And maybe even you implement this in PyAF, and we can take it automatically. It's just there. And then the next thing we're asking is what are the processes? Okay, because the processes represent the dynamics of the plant. But again, we're not asking what's going to fail. We're asking, what does your plant do? How, and then what are the sub-processes for doing that? And sub-processes and sub-processes. Now, at every level, you only need to think about this specific process and this specific part. So actually, it's very, very simple way of describing the processes, describing the parts, making the links between them just by drag and drop, and thinking only about this specific area where you're running now. Okay, so and we worked really hard to make it simple. So actually, in some cases, even a junior process engineer have sufficient knowledge with help here and there from P&IDs, here and there from more experienced engineer in order to build the model. Now, the other aspect of this is that it's it's the first time this knowledge is captured somewhere. Okay, think of the situation where there is this rotation, and now a guy comes in, he knows everything and then after 2 years he's leaving to another position, and there is a new guy, he doesn't know anything. Now he needs to address all these problems that are occurring in the plant. And I think one of the values that you're getting here is that it's captured in a way which is understandable to people, which is formal, and which you can always add more and more details to, okay? But at the same time, preserve your knowledge for the use of the machine learning. It's not something that you built once and you cannot change it anymore, or a new person that comes in cannot affect it, or a new person that comes in doesn't know what the logic behind it. Everything is there and very organized and very formal. And of course, this is something we when we show a demo, there is a demo of this of the studio, and we show exactly how this model is built. And this is a process we did many times. It's a very structured process.
Where would you recommend to start trying the solution? What part of the plant?
Okay, the most important thing in this decision is to make it aligned with your with the KPIs of the project, with the effect that you want the project to have. So you know, doing project in a part of the plant which is maybe very important but doesn't have any problems, doesn't have any failures, doesn't have any, because it's so critical, would probably not prove the point. So you need to select a significant, the entire plant or a significant part of the plant in which in 3 months you're able to show some effect on the KPIs that you set into for the project. So if your KPI was, you know, I want to improve the quality, so you need to take a significant part of the plant, which if you improve the operation of that part, it will affect the quality. Or if you have uptime of the plant, you probably would want to select an area which has some kind of failures and is likely to fail within those 3 months. So your selection of area should be something that which is big enough in order to really affect the final results and show real value to the plant. It's not about analytics, it's not about statistics, it's about value.
Okay, Chen, thank you very much. Thank you all for joining us. You will get a recording of the webinar to your email, and please feel free to ask any more questions if you have them. Thank you. Bye-bye.
Okay, thank you all.